chiral perturbation theory is an effective field theory constructed with a Lagrangian consistent with the chiral symmetry of quantum chromodynamics, as well as the other symmetries of parity and charge conjugation. ChPT is a theory which allows one to study the low-energy dynamics of QCD. As QCD becomes non-perturbative at low energy, it is impossible to use perturbative methods to extract information from the partition function of QCD. Lattice QCD is one alternative method that has proved successful in extracting non-perturbative information. In the low-energy regime of QCD, the degrees of freedom are no longer quarks and gluons, but rather hadrons. This is a result of confinement. If one could solve the QCD partition function, then one could extract information about low-energy physics. To date, this has not been accomplished. A low-energy effective theory with hadrons as the fundamental degrees of freedom is a possible solution. According to Steven Weinberg, an effective theory can be useful if one writes down all terms consistent with the symmetries of the parent theory. In general, there are an infinite number of terms which meet this requirement. Therefore, in order to make any physical predictions, one assigns the theory a power counting scheme which organizes terms by a pre-specified degree of importance, which allows one to keep some terms and reject all others as higher-order corrections which can be safely neglected. In addition, unknown coupling constants, also called low-energy constants, are associated with terms in the Lagrangian that can be determined by fitting to experimental data or be derived from underlying theory. There are several power counting schemes in ChPT. The most widely used one is the expansion. However, there also exist the and expansions. All of these expansions are valid in finite volume. Particular choices of finite volumes require one to use different reorganizations of the chiral theory in order to correctly understand the physics. These different reorganizations correspond to the different power counting schemes. The Lagrangian of the expansion is constructed by introducing every interaction of particles which is not excluded by symmetry, and then ordering them based on the number of momentum and mass powers. It is also common to compress the Lagrangian by replacing the single pion fields in each term with an infinite series of all possible combinations of pion fields. One of the most common choices is where MEV. In general, different choices of the normalization for exist, and one must choose the value that is consistent with the charged pion decay rate. The theory allows the description of interactions between pions, and between pions and nucleons. ChPT can also describe interactions of kaons and atomesons, while similar theories can be used to describe the vector mesons. Since chiral perturbation theory assumes chiral symmetry, and therefore massless quarks, it cannot be used to model interactions of the heavier quarks. For NSU theory, the leading order chiral Lagrangian is given by where MEV and as the quark mass matrix. In the expansion of ChPT, the small expansion parameters are where is the chiral symmetry breaking scale, of order 1 GeV. In this expansion, counts as because to leading order in the chiral expansion. Behavior of current divergences under SU_3 times SU_3. Physical Review 175, 2195. Bibcode 1968 PHRV 175.2195 G. DOI 10.1103, FASREV 175.2195. The effective theory in general is non-renormalizable, however given a particular power counting scheme in ChPT, the effective theory is renormalizable at a given order in the chiral expansion. For example, if one wishes to compute an observable 2, then one must compute the contact terms that come from the Lagrangian versus SU theory at tree level and the one-loop contributions from the Lagrangian. One can easily see that a one-loop contribution from the Lagrangian counts is by noting that the integration measure counts is the propagator counts as, while the derivative contributions count as. Therefore, since the calculation is valid, 2. One removes the divergences in the calculation with the renormalization of the low-energy constants from the Lagrangian. Therefore, if one wishes to remove all the divergences in the computation of a given observable 2, one uses the coupling constants in the expression for the Lagrangian to remove those divergences. In some cases, chiral perturbation theory has been successful in describing the interactions between hadrons in the non-perturbative regime of the strong interaction. For instance, it can be applied to few nucleon systems, and at next to leading order in the perturbative expansion. It can account for 3 nucleon forces in a natural way.